Here is some logarithmic footage straight from the camera. Here it is being fixed with one of my logarithmic LUTs. Many cameras can save their footage using various profiles, including logarithmic profiles. Here, for example, are the profiles used by the Zcam E2 cameras. Note especially the flat profile with the same dynamic, I assume, range as Zlog2, but with color correction. And since Zcam knows the inner workings of their cameras, they can presumably color correct better than any of us, though we can still color grade it. Sadly, their OFX plugin doesn't support Vegas Pro at this time, despite supporting Resolve by their biggest competitor. And I could never get their LUTs to give me satisfactory results. So I wrote my own LUTs, which work despite their vague words on the documentation page you're looking at. Let me explain. Logarithms are the inverse of the exponentiation function. The basic exponentiation looks like this: a raised to the power of y. Not to be confused with power function, where y is raised to the power of a. Please note that x and y are variables, while a is a constant. Though being a constant in exponentiation, a can be any real number, or even an imaginary or complex number, but here we will only deal with real numbers. We, however, are interested in the inverse of exponentiation, which is only invertible if a is a positive number other than 1. By that I mean the number 1. A cannot be 1. So by inverting exponentiation, we get logarithm. Y is the logarithm of x with a base of a. If that's confusing, try substituting the exponentiation for the x in the logarithm. Though we do not normally do that because we do not know the value of y. Normally we know the a and the x, from which we calculate the y. That brings us to our first problem with logarithmic footage of Zcam and other cameras. What base a was used to produce the logarithms? Despite some misguided claims on the web, different bases produce different curves. Just compare the same footage adjusted with the assumption that a equals 2 in the top left and with a equals 10 in the bottom right. They look quite different. Which one, if any, is right? In image color processing, we tend to normalize the values of the RGB channels to the range of 0 through 1. With 0 and 1 included in the range. This has the wonderful advantage that we can create numerous functions, y equals f of x, such that for x equals 0 we get y equals 0, and for x equals 1 we get y equals 1. And for any other x within the 0 through 1 range, we get a y within the 0 through 1 range. Alas, logarithm is not one of those functions, and neither is exponentiation. Consider the exponentiation again. We've determined that one of the conditions of its invertibility is that a is positive. But then, no matter the value of y, x is also positive. X is never negative. More importantly, x is never 0. Therefore, there is no logarithm of x equals 0. But obviously, logarithmic footage exists. Instead of trying to figure out the y for x equals 0, let's figure out the x for y equals 0. If we raise any invertible a to y equals 0, we get x equals 1. If we invert it, we get the logarithm of 1 at any base a is 0. Similarly, we can figure out the x for y equals 1. In this case, however, the result depends on the value of a. The a raised to the power of 1 is still the a. Inverting that, we get the logarithm of a, where the base a is 1. All we need to do now is to calculate logarithm of 1 for x equals 0 and logarithm of a for x equals 1. For that, we will use an additional variable. Let's call it z, such that z equals 1 when x equals 0 and z equals a when x equals 1. And that is just a basic linear function z equals 1 plus x times a minus 1. So if x equals 0, z equals 1 plus 0 times a minus 1, which equals 1. And if x equals 1, z equals 1 plus 1 times a minus 1, which equals 1 plus a minus 1, which equals a. Substituting z for x is one of the ways cameras can produce logarithmic footage. This is the most likely way, so we leave the others to a later video. Of course, now we need to figure out how to convert logarithmic footage to something we can present to others. That is simple. Just as the logarithm is the inverse of exponentiation, exponentiation is the inverse of logarithm. Indeed, the exponentiation is sometimes called the anti-logarithm, that despite the fact exponentiation has been around for thousands of years, while logarithm was discovered in the 17th century. At any rate, if we know the base a, we just raise it to the values in the pixels to get z. And since we know how to convert x to z, we can convert z to x. But what if a equal 1, you might ask? Well, that wouldn't work, would it? Luckily, we have determined there is no such thing as a logarithm when the base of a equals 1, so we're good to go. That's it for now. As always, I remain. Hasta la pasta.